Welcome to Atmos, the tutorial, step one or part one, running the model. Before we get started, you'll need a few things. You'll need a computer with a terminal environment. Inside that terminal environment, you will need a Fortran compiler. gfortran or GCC is the free version of that. And you'll obviously need Atmos, the model, which you can get from Bitbucket if you're on our team or from GitHub if you're not. So get all that together, come back, open up your terminal into the Atmos folder, and then you can follow along as I show you how to run the code. What you're going to want to do to run the code, once you have it and all the things you need to run it installed, is go into the main file. We try to, but aren't perfect at having things in all caps if they're a folder with other things inside of it. So these are all folders here. And then we try to use camel case for other things like executable scripts or the files themselves. The code itself is in Fortran, and the Fortran files with the code in it all end in star.f. So what you see here, we have two codes that are part of Atmos. We have a photolysis code, and the main file for that code is photomain.f. There are also subroutines that are in their own Fortran files that are in the subdirectory photochem, and then a subdirectory within there called subroutines. When you tie those all together with a make file called photomake, you get an executable. That executable is photo.run, which is not showing up here because this is a fresh install and I haven't made that yet. I'll show you how to do that in a moment. We also have a climate code. The main file for that is climate-main.f. There are also subroutines that are inside the climate folder, and the climate make file ties all those together into a climate.run executable to run the climate code. You can also couple these two codes together, and the reason that's sort of what Atmos is when you're running them in fully coupled. And the way we do that is we run the photolysis code, and then the climate code, and then the photolysis code, and then the climate code back and forth. And what that gives you is the photolysis code is predicting the concentrations of a bunch of gases as well as some aerosol species as a function of altitude. And then the climate model is predicting the temperature profile, the temperature as a function of altitude. And we pass that information back and forth because the greenhouse gases that the photolysis code predicts can impact the climate, as can the aerosols, the presence of aerosols that are predicted by the photolysis code. Conversely, the temperature profile that the climate code predicts can impact the abundance of those gases and those aerosols, especially for the aerosols. And so by running the two back and forth, one after the other, we can usually get the code to converge to a state where all of that is self-consistent. The temperature profile is consistent with the gas profiles and the aerosol profiles, and that those gas and aerosol profiles are also consistent with the temperature profile. And that is a good way to think of how to use this code. It is not a way to find an answer for what a specific planet is or was like. But it is a way to find out a self-consistent way that planets could exist and exist on geological timescales or astronomical timescales. So I think of it as finding self-consistent conditions for planets, not specific incarnations of planets that must exist in the universe or must have existed in Earth history or Martian history. Okay, so with that, let me just show you how to use the code at a very basic level. And then once I show you how to do that, I'm going to dive deeper in. And I'm actually, for this tutorial, I'm just going to talk about the photolysis code. One note on the climate code, it's only really good for planets in the habitable zone, specifically Earth-sized planets in the habitable zone. It's not currently flexible to simulate gas giants or Venus-like worlds or iced over planets. It really is only good for Earth-sized rocky planets in the habitable zone. The photolysis code, on the other hand, that can simulate a wider variety of planets. We've done hot Jupiters with that code. We haven't published on that yet, but that's in the works. We haven't published on, but are working on a Titan module for the Titan template for the photolysis code. Historically, it's been used more for publications on ancient Earth when the Earth was much less oxidized than it is now, more reducing than it is today, had a very different atmospheric composition with a lot less oxygen in the atmosphere. We've also used it for Mars, research on both modern and ancient Mars, and for exoplanets with a variety of sizes and chemical compositions. We'll get into that in a little bit when we talk about input files. Okay, so again, back to running the code. There's two ways to run the code. I recommend that when you're starting out, you use this script here, run models.sh. There's a few reasons I suggest you start there. One is you don't have to understand all the details of something called make files, which is what I'll talk about in a minute, which is this photo make. You just have to be able to run this, and it should automate a lot of the compiling for you, and it also will automate moving input files around for you in a way that doesn't require you to fully understand how to move everything around. Eventually, if you want to be an expert user, you're going to want to move to a more manual, hands-on approach. But when you're starting out, just do this. By the way, this // for very beginners is I want to execute the thing that follows the slash. So // run models.sh will run models.sh. And this will show you an interactive environment in which it tells you first which templates we have. Templates are basically ready-made, self-consistent solutions for atmospheres for a variety of compositions. And what this represents is that Archean plus haze, for example, has all of the input files one would need to run an Archean-like world with haze in it. Archean plus low haze is the same thing, but with a thin haze, an Archean-like world. Archean is an ancient Earth-like world with a low amount of haze in it. Archean haze plus K6V is that first planet, but around a K-type star. So it's an Archean-like planet with a haze around a K-star. Archean S-Org plus haze is Archean-like world, including sulfur organic chemistry. This is relevant to some specific problems on Archean Earth, and it also could have an impact on the haze thickness. Mars modern plus chlorine is a modern Mars template, but it also includes chlorine chemistry. That's what this CL is. Modern Earth is modern Earth. Modern Earth plus CL is modern Earth with chlorine chemistry included. So that by implication, modern Earth without plus CL does not have chlorine chemistry included. Proterozoic is a sort of middle period, a middle eon in Earth history that has a moderate amount of oxygen. And within Proterozoic Earth, there's sort of different geological or geochemical constraints suggesting that it had a relatively high amount of oxygen within that moderate range, or a relatively low amount of oxygen within that moderate range of oxygen. So that's what these represent. And then high O2 templates, this is for atmospheres that have lost a lot of hydrogen through the top of the atmosphere, leaving oxygen behind, and they might be oxygen dominated as a result. So these are all folders effectively within our templates folder. Each one of these is sort of ready to go, and it should compile and run quickly. If that doesn't happen, that's most likely because there's a bug somewhere that we have in the code that we need to fix. And if that happens, get in touch with us, and we'll see if we can either give you a workaround or a fix for that problem. Okay, so if I wanted to run Archean S-Org plus haze, which for my own research is the one that I've probably used the most historically, I would type that exact phrase. I believe this is case sensitive, not sure, but I always make this case sensitive just to be safe. You just enter in whichever template you want to run exactly as it's written above, and you press enter. And then what the model does, or what this script does, is it copies all of these input files into the proper location they need to be to run the code. So as we'll talk about in a little bit, in.dist, input photochem.dat, reactions.rx, parameters.inc, species.dat, and planet.dat, those are the input files you need to run the code. And these specific input files are these specific versions of the input files correspond to this template, running an Archean-like world with organic sulfur chemistry included, as well as a photochemical haze. So after it copies the files, the next thing it's going to ask is, do you want to compile photochem? The first time you run the code, you will have to do this. I strongly recommend doing this anytime you switch templates. If you have not switched templates and you've already run the code, you don't have to recompile photochem. And the reason is that all these input files, and in particular reactions.rx and species.dat and planet.dat, these have things you might want to change between runs. You might want to change the gas concentration or the star type, or a reaction rate constant. If you want to do those things, you can make those changes in the input file, and you don't have to recompile the code. But actually, to back up a step, what compiling the code is doing is it's taking the fortran files, and turning them into an executable code. So if you change the fortran, you're going to have to recompile. If you change the parameters in the code, the number, which we'll show later, like the number of reactions, the number of species, things like that, because of the way that Fortran handles vectors, or at least the version of Fortran we use here handles vectors, you'll have to recompile the code. But if you're not changing the formal Fortran code or like the number of reactions or the number of species or the height of the atmosphere or the number of layers, if you're not changing any of those vector sizes, which are all contained in parameters.inc or in the Fortran code, you don't have to recompile. So in other words, if I've run Archean SORD plus haze already, and I've just changed like the methane concentration or the star type, I do not have to recompile. And that saves time, especially when you're scripting over a large parameter space. So in this case, like I said, I haven't run the code before, or if I've switched to template, I do want to recompile. And then this is basically showing you the compilation of the main code. And what this does is it takes each of the individual subroutines, which are in individual star.f files, compiles them into their own executables, which are these .o files here, which are in this folder, photochem/object files. And then it stitches them together into a single executable called photo.run, this file here. Now you could do this all manually. You could, in theory, copy all the input files together and then run the make file and then execute. The script is just a shortcut way to do that. So now it says, would you like to run photochem? I'm going to say yes. And now it's running the code. What it's showing here is the time stepper. This is the control on how well converged the model is. This is not particularly well converged. It's pretty well converged, but not perfect. So there may be something we need to change in there in the code or in the template. And this is now a successfully completed run. It completed after 97 time steps. You can see it ran for a model time of about 10 to the 18th seconds, with the final time step predicted to be 5 times 10 to the 18th seconds. It's like the age of the universe. And what this is showing in the time stepper is it's showing you the time step. It's showing you how the relative change, so the change in predicted concentration divided by the absolute concentration for the least stable species. So it actually calculates that relative change, the change in concentration over the absolute concentration for every species in every layer. And then whichever is the least stable, so the maximum relative change, it then prints out the information on that because it's the least stable one that determines the time step. It says it's it gives you, this is the relative change for the least stable molecule. This is the least stable molecule. In this case, at the end of the model run, it's H2O2 at this layer of the altitude in centimeters. This is a concentration of that species at that layer and the predicted change for that species in that layer. This is the current time step, and this is the current model runtime. And what should happen is we use a reverse Euler method to take the time step at the beginning of a model run, which is in microseconds, all the way up to the age of the universe. And what happens is every time step, the model says, what's my least stable molecule and how stable is it? If it's not stable, then the model time step will decrease or stay the same, most likely decrease if it's very unstable. If the code is stable, in other words, if the greatest change of any particular molecule is relatively small, which in this case it was for basically the entire run, the time step will get larger. And if you think about that, what the code is saying is like, okay, I took a time step, nothing changed that much, so I can be bolder and take a bigger time step. That's not the mathematical way of phrasing it. It's kind of anthropomorphizing the model, but that's what it does. If things are stable, it takes a bigger time step the next time step. And if it's still stable, it continues to take a bigger and bigger and bigger time step until those time steps are the age of the universe. And if things are still stable then the code says, okay, I have found a solution that is stable over geological timescales as long as the inputs are also stable over, at least in a time average sense, over geological timescales. And then it stops and it gives you a bunch of diagnostic information on the atmosphere. And then it says, would you like to recompile Clima? In this case, I'm not going to do that because this tutorial is about photochem. And then it says, would you like to run Clima? I'm going to say no again. And this is where we're going to stop, because I ran out of time for how long of a video I could upload to YouTube without being some, like, I don't know, blue check mark person thingy with a big YouTube account. So It's actually a good place to stop. You know how to use the model now.